Okay. So far, regroup. So far, what kind of motion have we done so far? What's the easiest kind of motion ever? Linear motion. And we've done these for basically all of kinematics. Okay, every single thing we learned in kinematics had to do with what? With linear motion. Even when something turned, we only cared about when it was going linearly first, and then when it was going linearly final as well. Okay. Then we started doing what? Nonlinear motion. So far, what was the only nonlinear kind of motion we did in kinematics? No. Technically, relative was still linear. You just got shifted over, like like pushed. Say projectile motion, because it followed a what? It followed a parabola. Basically, that's why we use what? We sometimes use the quadratic equation to solve what? To solve the projectile motion. This this is the last kind of what? Of nonlinear motion we have, which is circular motion. Okay? So suppose an object undergoes some motion such that the path is, and here's the thing, it has to be a what? It has to be a perfect circle. Okay? It has to be a perfect circle. Okay? In only such a case, the motion of the object is classified as circular motion because it goes in a circle. Okay? However, everyone, we will still cover, technically, we could still cover any motion, even if it's not what? Fully circular, as long as one section of the object is what? Is a circular. Okay? So, okay, not in grade 12 though, but in first year, yes, you will basically do like, for example, look at an object that moves like this and then turns in like a quarter of a circle and then goes linearly again, and maybe it turns again in 3/4 of a circle and then goes linearly again. So as long as what? As long as a section of the motion is a circle, that part of the motion is classified as what? As a circular motion. Okay. How about if it looks like a different kind of sorry, a curve? Aside from obviously projectile, because that looks like a perfect parabola. What if it looks like a cubic? Or what if it looks like a sine or a cosine wave? That needs calculus to do it. That's why we don't do it in what? In grade 12 physics. But you do it sometimes in first year. Okay? Okay. So, in other words, as long as some section of the object's motion looks exactly like a part of a circle, the equations we will learn next apply to that section of the motion, but not to the rest of it. What could apply to the rest of it? I don't know. If it's linear, maybe kinematic equations. If it's a projectile, maybe the projectile equation. We don't care. But as long as it's a circle, today's equations apply. Okay? All right. Okay, so as long as looks exactly like a part of a circle. How much of a circle? I don't care. A single degree or 359 degrees. Who cares? Okay. So let's go to the next slide. You don't have to copy much, actually, I think, for the next slide. So basically, this is a perfect what? That one is linear first, and then turns, and then goes like this. So all of these, whenever what? Whenever you can perfectly see that there is a circular part of the motion, that what? That here, because technically, can you imagine a full circle from this? Yes, you can. Basically, right here, right here, right here, and right here as well. Okay? So those red sections, definitely what? We can apply today's equations to it. Only those red sections. Okay. So we have to learn a new word today. Okay? Who can say that first word? Try to break it down into two, because it actually, Latin-wise, it's actually broken down into two. Centripetal. So centripetal. Okay? Centripetal, yes. So get used to this one. Okay? Centripetal, you're always going to hear it in both this unit and whenever you talk about anything that what? Spins in a perfect circle. Centripetal. Okay? So whenever an object moves in a circular path, remember, okay, everyone, question for you. Just right off the bat here. If something moves in a circle, could it be Newton's first law? If something moves in a circle, does it qualify under one of the two cases for Newton's first law? Okay, remind me again, what are the only two cases that Newton's first law cover? Only two cases. at rest, which obviously is not here because something is moving, or constant motion in a straight line. Remember, yes, everyone, remember, when I know that's the problem. You think of it as constant speed. It's not constant speed. It's constant what? The velocity, which means it's a constant what? Vector. So remember, Newton's first law either covers what? At rest or uniform motion in a constant straight line. Obviously, this is going what? This is going in a what? So right off the bat, it is definitely what? It is definitely not Newton's first law. Which means what? Anything that's not covered by Newton's first law is always covered by Newton's what? Second law, okay? You might say, how about third law? Third law is a special case. Third law is not really much of a motion one. It's a what? It's an action versus what? Reaction, exactly. It's not really motion. It's an action pair of forces. So whenever an object moves in a circular path, it's not Newton's first law. It has to be Newton's second law. What's the form of Newton's second law? F net equals m a. So there's got to be an acceleration. One component of its acceleration, that is the one making it turn around, is always pulling it what? Outside or inside? When you want to turn in a circle, are you always going out or inward? You're always going in because you're trying to what? It's as if you're trying to spiral, but you never make it to the what? You never make it to the center. Exactly. So you're always being pulled what? You're always being pulled in. I'll give you an example. One of the easy examples, actually, that I always use, basically, this right here. Can I spin this? Yes, I can. What force are on basically the earpiece right here? Is it pulling out or pulling it in? It's okay. It's always trying to make it go where? To the center, which means what? It's trying to what? Push it out or take it inside towards the center. Exactly. So centripetal acceleration always points where? Out or in? Always towards the inside of the circle, which is interesting because the Latin name centripetal is made up of two words. Century means what? What does century mean? Center, exactly. And pedis means what? To seek, which means what? You're always seeking the what? The center. You're always seeking the center. That's why centripetal acceleration in any FBD you ever sketch in grade 12 or first year is always going to point to the inside of the circle, not just to the inside, perfectly towards the what? Perfectly towards the center. Centripetal, always going towards the center. Okay? All right. What is the symbol for centripetal acceleration? Well, obviously, it's acceleration, so it has to still be what? A. But it's a very specific kind. We have to use a subscript. It's what? AC. Both A small, everyone. It's A small because it's still what? It's still acceleration, never A capital. A capital is usually like area or amplitude or something like that. Small a is always acceleration, okay? AC. Do you ever need to give me a direction? Not really, because you just showed me a what? Whenever you show me a diagram, that means you've already took the direction out of the problem. I just need the magnitude, okay? There we go. So do me a favor here and put C here, put C here, and put C here as well. Okay? But by the way, just so you know, everyone, centripetal acceleration is still technically just a very special case of what? Of Newton's second law. The only difference is it applies to a very special kind of motion, which is perfect circular motion. Okay? So everyone go ahead and put C here, small c, or big C. Small c here. Oops, sorry. Small c, small c. What do you think V means? Velocity, or could be what here? Could be speed. So everyone, question for you. How many people here, raise your hand, if you heard the word, you have to have heard it so far, both in grade 11, but especially if you've been doing calculus. The word tangent. Can someone explain to us what the word tangent means in calculus? In calculus. Forget physics, in calculus. What does the word tangent mean? What's a tangent line to a curve? Any tangent line to any curve. Ammar. Everyone, is this a line or a curve? Right there. That's a curve. if I ask, Wadah, come up. Wadah, I'm going to ask you to sketch in black. Go ahead. Sketch for us the tangent line to this curve. Add that blue dot right there. Oh, it's not working? Sorry. Oh, go ahead with the blue. What do you think he's trying to do to the best of his ability? Ammar. The line only touches slope at and 1 point, such that does it cut through it or does it just graze it? Exactly. Tangent lines always what? Always graze. By the way, technically, if you extended that, keep going, extending it below. Is it going to eventually cut the curve? Is that still okay? Yeah, but does it matter that it cuts the curve at a different point than the tangent point? No, because the curve could still be what? Going all over the place. Is it making sense? So the problem with so many people thinking is that, oh, wait a minute, a tangent line only touches the point at what? 1 point. Not necessarily. That depends on the what? That depends on the curve itself. But you know it touches it at 1 point at such a what? What's the word again I used? It what? It grazes. When you graze something, you just go and you just what? And you just touch it. That's how tangent lines always work. Perfect. Thank you, my friend. Awesome. All right. Okay. Does this look like a tangent line, everyone? The green one. Does the green one look like tangent? Yes. Whenever you have a circle, everyone, whenever you have a circle and you go here, the tangent line is always going to look like this, right? It should touch. Perfectly, it should touch. How about the AC? Is it tangent? No. What do you call something that points between the center and the edge of the circle? Radius, exactly. So always know your your velocity is what? Is tangent. But your acceleration is what? Radius. There you go. Now you got it. Okay, so let's actually put these on the diagram. So I want you just to point to one of the velocities and just say tangent, tangent, while this one is radius. They have names for them in physics. Velocity is called the tangential part, and acceleration, centripetal, is called the radial part. Radial means it's along the radius. Tangential means it's along the tangent. Okay, so velocity is always a tangent, and radius is always a radius. By the way, does it make sense for velocity to point this way? Everyone, if I am spinning this, where is it? Yes. Everyone, question. Bless you. Everyone, if I'm spinning this and I let go exactly at the moment when the earbuds are right here, would they move up or that way? How many people say that way? Is that tangential? Of course it is. Because if you let go at any point, the thing never moves in. It moves what? It moves what? It moves away or out. Exactly as a what? As a tangent. So things always move according to the what? According to what? Velocity, not according to what? What does acceleration just do? Pulls it where? Always in. Velocity is just what happens once the what? Once the thing is what? Released. Perfect. Yes, you got it. These are the most two important thing about centripetal motion. Velocity always drives away. Centripetal acceleration always pulls in. Okay? All right. So here's the equation that we need to know for today. So the mathematical formula for the magnitude, again, diagram, it's done. We know it's pointing in. You just have to point towards the center of the circle. The mathematical formula for the magnitude of centripetal acceleration is, what's the first thing in the fraction? What's the first thing in the fraction? Sorry, like the numerator of the fraction. The speed of what? Rotation. How fast is it spinning? But divided by what though? Divided by the radius of the hypothetical circle if you what? If you imagined it to be complete. Assuming, by the way, again, sometimes circular motion could be a part of a circle or a full circle. If it's a full circle, great, we can see the radius. If it's not a full circle, we have to kind of imagine it full, and then just what, see how big the full revolution is. Okay, and this is one of the most important equations in what, in motion physics. AC equals v squared over what, r, which is the radius. Sometimes they call it small r. I like to call it capital R. Okay, v squared over r. I have a question for you. What's the first thing whenever they come up with an equation? What's the first thing they always check? Always, just to make sure that it at least makes logical sense. Units. Thank you, everyone. Let's check the units here. What's the standard unit for speed? Just speed, back from kinematics. Meters per second. So technically, the unit for this guy is meter per second, but it's being what? It's being squared, divided by radius is just a what? It's a length, it's a size of a line, so that means what? It's in meters. Okay? Who can tell me how to simplify this fraction? Ahmed, go ahead. What do I do first? So m squared over s squared, all divided by m. But technically, this m has a what under it? A 1, our best friend when it comes to what? Dividing fractions, which is equal to m squared over s squared times what? 1 over. What happens to an m here and an m here? Cancel. And what's your final answer? Indeed, it is, at the end of the day, acceleration inward. Acceleration inward. That makes perfect sense. Okay? Okay. Okay, everyone. How many things apparently can I change about this diagram? Only 2 things. What and what? Speed and radius. Okay. What can you say about this object? It has a very what speed? Very low speed, but a very big what? So is it going to spin very fast or very slowly? This is like you what? Swirling something, but very what? With a huge tension or with a small amount of tension? With a by the way, I'm using the word tension because tomorrow we're going to do centripetal force. We're actually going to calculate how much, not just acceleration, how much force is physically pulling it in. Okay? All right. How about if I go to the extreme? Very small, but very what? What do you expect the speed of revolution now to be? Very, very. This is like what? Spinning what? With a low tension or with a high tension? With a high tension, because it's being accelerated inward very quickly, and that's why it can finish a revolution very quickly as well. Okay? All right. Same thing here. Let me just zoom out. Sorry. You can make it go clockwise or counterclockwise. Interesting. Let's stop it for a second. Everyone, right here, if you let go, how is this dot gonna go? In or away? Away. So that's what, is that radial or tangential? Tangential, because it's basically, you cut here, it just goes away. However, which way is it always being pulled? In. That's why it's basically what? It's trying infinitely to what? Not infinitely. It's trying forever to finish the what? To go into the center, but it can't. Why? Because it's being kept at a what? At a constant radius the whole time. It's trying to spiral in, but it never does. Okay? Awesome. All right. Okay. How many people heard those words before, whether in physics or in math? How many people heard them in grade 11 physics last term? You had to. Do you remember what kind of topic we finished in grade 11 physics that had to do a lot? It was actually centered on frequency and period. Starts with W. Waves. Every wave has a what? Has a what? Must have a what? Must have a period and also 2 other things. Do you remember them? We're not going to cover them now. We're going to cover them when we get to actual waves and light, not waves and sound. Waves and light in grade 12, waves and sound in grade 11. What was the other thing? Amplitude, and one more thing. Wave length, how big the wave is. Okay? Well, today we're only going to focus on what? Frequency and period. Okay? So technically, whenever something repeats itself, it has what and what? Frequent. Whenever anything repeats, is a circle repeating? Yes, it is all the time, which means what? It is an example of what? Of a periodic motion. Periodic motion. You definitely you heard that in what? You heard that in grade 11 functions when you did waves, and you definitely heard it in grade 12 functions when you also did sine and cosine waves. The only way to study periodic motion is to become basically an expert in sine and cosine waves. Okay? So periodic motion always have two related properties, such that if you know one, here's the good news. You immediately can figure out the other with a very small calculation. I'll show you how. So those properties are called frequency and period. Go ahead, copy these down. Frequency and period. And get used to this name, please. Periodic motion. Do not call it repeating motion. I know that's the descriptive name, but the official scientific name is periodic motion because it has a period. Okay? So get used to periodic motion. Anyone here who will ever major in electrical engineering will basically become an expert of periodic motion. Why? Because electrical engineers deal with what? Deal with alternating currents and signals and voltages, and all the time they are what? Going up and down, up and down, up and down, up and down, which means what? It's a wave. Also, anyone here who might become a computer scientist or a telecommunications engineer, you will be dealing with like signals and electromagnetic frequency. Boom, right there. Okay. All right. So let's talk about period of rotation. Okay. So when an object moves in a circular path, the period. What's a period of a certain event? It's the time it takes to do the event. How many times? Once and exactly once. Never go more than once. Never go less than once. If you go more than once, that's longer than a period. If you go less than once, that's shorter than a period. Okay. So it is the amount of time, and make sure you focus on the word amount. It's a positive amount of time. No period is negative. It's an amount of time it takes an object to make a single full revolution. That's the circular motion definition. The general definition is it's the time it takes an event to repeat itself once. Well, if you're spinning, that means it's the time that it takes to spin to spin something only once. Okay? One full revolution. By the way, everyone, don't say rotation. How many people know the difference between revolution and rotation? I did not know the difference until like maybe 5 or 6 years ago. I usually just use the word interchangeably. But what's the difference between revolution and rotation? Does anyone know? It's a very subtle difference, but it's important. And that's why we use the word revolution usually more than rotation. You know? Well, you can complete a rotation too. Ammar? Yes? How about revolution? Everyone, rotation usually is what? An object and it's what? Spinning. Thank you. Revolution could be that or what? Something revolving around. So is the Earth rotating around the sun or revolving around the sun? Revolving, because it's what? It's not exactly what at the center of rotation. It's away and it's going this way. Yes, revolution is the term for anything generally that goes around something else. Okay? All right. Who remembers the symbol for period from grade 11? No, F is frequency. Technically, I just told you the next one. What is it for period? And I'll give you a hint. It's not P, because P is used for a bunch of other things. Capital P is used for something else. Lowercase p is used for something else. Who remembers the symbol for period from grade 11 physics? I'll give you a hint. It's really just an amount of what? It's an amount of what? Time. What's the symbol for time? T. But this is a very special amount of time. It's the time it takes to revolve once. So instead of small t, we're going to use what? There you go. You got it. Always in physics, capital T is period or temperature. But we're not going to do anything with temperature in this course. So every single time we're going to see capital T in this course, it's either going to be tension or temperature. Sorry, period. So don't worry about that. Again, I mean, sometimes they have to use the same symbol for a bunch of different things. It just depends on the context. What are you studying? Okay? So it's just an amount of time. So what do you think the unit is for period? There you go. Second. Does anyone remember another name for a single event? Starts with C. Does anyone remember from grade 11 the name? What do you call a single vibration or a single oscillation or a single wave like up and down? It starts with a C. When something repeats a lot, what other words can you call it? What do some people write to school sometimes? A bicycle. When something cycles, that means what? No, but seriously, what do you call it? It's called bicycle. Bicycle, because it's got 2 wheels. What's the other thing that got 3 wheels? Tricycle. Tricycle. That means what? A cycle is just a what? A single revolution. So a cycle takes how much time to happen? A single what? A single period is the time it takes to repeat a cycle once. Okay, and it's only okay. That was okay, everyone. That's why I'm talking about cycle. Does it make sense to say? Listen up. Does it make sense? Does it make sense to say this revolution took? Sorry, the period of this revolution is 5 seconds per cycle. Do you think that you need to say per cycle when you say the word period? No. Why? Because exactly a period already covers how many? One single cycle. So you saying the period of this behavior is 5 seconds per cycle is a redundant statement. You've already said what? Period, which means you're only talking about how many cycles. So never say per cycle. Just say 5 seconds or whatever amount of time. Okay? All right. Okay, pencils down, everyone. So did it move? It did. In what kind of path? Perfect circle. What do you call the perimeter of a circle? Or the length of a circle if you cut and expand? Circumference. Thank you. Does anyone here remember the equation for the circumference of a circle? Come on, you're in grade 11/12. Okay, there's a pi involved. Okay, there are 2 ways to say it. Listen up. There are 2 ways to say it. That's the area. Remember, everyone, when there's a square, it's a 2-dimension. It's like an area. When there's a cube, it's a what? 3-dimension. It's a volume. When there's no cube or no square, it's a what? It's a linear, which is a length. Okay, always remember that way. When you want area, you go squared. When you want volume, you go cube. When you want length, you go linear. You go with the power of 1. What did you say? He said pi d. What do you think d means in his equation? Which is? No, not r squared. 2r. What is the double of radius? Diameter. So there are 2 ways to say the equation. Either pi d, or pi times the diameter, or 2 pi r, which is pi times 2r, because a diameter is what? Twice the radius. Which one do you think is more common? 2 pi r, actually. Yes. Everyone, I open any physics or math textbook, especially advanced one like in first year and beyond, almost no mention of diameter is mentioned. It's always what? Radius. Everything is based on radius. Okay? All right. Go ahead. C equals 2 pi r. Okay. By the way, you can call it small r or capital R. Let's just call it small r for now. I know I gave you capital R for the equation. Doesn't really make a difference. All right? Okay, everyone, question for you. If I told you, listen up, pencils down. If I told you this circle has a radius of 6 centimeters, again, don't copy anything. I'm just giving you an example. This circle has a radius of 6 centimeters, and the time it took that orange ball to go 1 full revolution was 5 seconds. Can you tell me how fast it's going? Okay, again, I gave you the radius, I gave you the time, and I'm asking you for speed. By the way, just a question for you here. Are we going to assume any acceleration or deceleration here? Nope. Everyone, everything in the circular motion unit or section is completely constant speed, just to make it easy. So if you're always using, if you're always considering constant motion, what equation do you always use? What equation do you always use when you're talking about an object moving with a constant speed, even though that speed is spinning? not going linearly, is spinning. What if I was going like this? Am I constant motion? Okay, what equation we always quickly apply to constant motion? The what? The triangle, right? Distance equals what? Speed times speed multiplied by time. Distance is always equal to speed times time. I just told you the time. I told you the time was 5 seconds. I didn't give you the distance though, but I did give you the radius. So what can you calculate? You can calculate the what? The diameter or just the radius, and then you calculate the circumference, and then you can tell me what? How fast it was going the whole time. As if you're taking a roundabout and you see the speed and you keep it at that speed. All right, perfect. Go ahead. So speed equals distance over time, as long as that speed is what? Constant. Thank you. Okay. Which means, as far as you're concerned, for a circle, that is 100% correct too. Which means this equation. Boom. We just related the speed of a what? Of a circular motion to both the size of the circle and the period it takes to revolve only once. Only once. What if you revolve twice? Well, you just also have to double the circumference. I'm assuming we are keeping the same rate of spinning. But we're always going to spin once. Okay? All right. So now we have a relation between V, R, and T. Good. Good. We're building up equations. Yes. Okay, you're right. What if it doesn't make a full revolution? But again, you need to know how much of a circle it covered, right? So think about it this way. If it, okay, a full revolution takes how much? A full T, right? Like a full period. How about half a revolution? Takes how much? Half a T, which will be what? Pi R only. So pi R over half a T. It's always the same ratio no matter what. Is it making sense? No way. Don't worry about it. Everyone. So, no, by the way, in first year, yes, you have to. Why? Because then, because then I could give you the T as a pi multiple and things cancel out nicely. You're right. 100%. Everyone, in first year, and probably in some calculus or grade 12 function, you can actually be given the period as a multiple or a scale of T, sorry, a scale of pi, and then you find that, oh, it cancels out nicely sometimes. Okay? But I'm just going to keep it to what regular decimal sig figs in this course. Okay? All right. Okay. Can I now play with this equation? What do I have now? What equation did we just create? An equation relating what to what to what? V to circumference to T, right? So can I now replace this with what I just created? Everyone, raise your hand. Do you think I can replace V now with 2 pi R over capital T? I sure can. What's the point of inventing an equation if you can sub it into another one? All right. So that means here it is. Go ahead. Just copy step by step. We're just deriving now. We are just deriving, not differentiating. Deriving. Deriving means you create an equation from another equation. So first, we went back to the original definition of centripetal acceleration, which is speed squared over r. And now I went back to the circle and got this equation and divided it by r. Technically, could this be simplified by a grade 10 student? Yes, you just have to keep your head straight through the what? Through the fraction. Okay, let's do it step by step. What does the square do to everything in the bracket? It squares every part. It attacks every part. So the 2 will be squared, the pi will be squared, the small r will be squared, and the T will be squared. So my next step would be that. And now we're back to what? Our best friend, the 1 under the R. Which means instead of dividing 2 fractions, we're going to what? We're going to multiply 2 fractions. But you have to pay the price of flipping the bottom one. What's going to happen now to a couple of the R's here? They have to cancel out. Not fully, partially, because only 1 power here and 2 powers here. So cancel, cancel. Yeah, I cancel a full R with only the 2. And now I have a what? I have an equation of AC that has nothing to do with the speed. Or does it? Technically, it still has to do with the speed. It's just not visible to you. Speed is still there. It's just been simplified. So now I can give you an equation. Sorry, I can give you a problem where I don't give you speed, but rather I give you the what? I give you the radius of the circle and the what? And the period it takes to revolve around that circle once. And then you can tell me how much centripetal acceleration is pulling it in. Or I could give you the AC and the T, and I ask you how big the circle is. Or I could give you the T and the AC, sorry, the R and AC, and I ask you how long it takes to spin it once or to revolve once. As long as you have everything but one variable, I have, it's fair game to be asked to what, to algebraically manipulate, cross multiply, and figure things out. You're in grade 12 now. Okay? All right. Now let's go to the next slide. Now let's talk about what? Frequency. Can someone tell me, if you remember from grade 11 physics, if something has a long period, does it have a high or a low frequency? So for example, everyone, was that frequent? Okay, how long did it take me to go up and down once? A long time or a short time? Which means what? If my frequency is high, my period is what? Very short. How about now? How about my period now? It's very what? It's very long, which means was I frequent or not that frequent? Which means if my period grows longer, what happens to my frequency? Perfect. So the frequency is basically what? The number of revolutions. Well, okay, technically, it's the number of events that happens in a second. However, because we're spinning, we can be very specific. We can say the number of revolutions or turns an object makes in 1 single second. 1 single second. By the way, you might notice I didn't say the number of full revolutions. Because is it always guaranteed you're going to finish a full integer number of revolutions in 1 second? No, you could finish 2 or 2.5 or 2.63, whatever. It just depends how fast you're spinning. So I'm just going to say the number of revolutions. Ahmed, what was the symbol for frequency? Capital or small? Because we used a capital for what? For the force names. Perfect. Everyone, always lowercase f. And I remember from grade 11, some people saw this and they were like, does it have to be a fancy f? You have a low bar for fancy if you think this is fancy. This is not fancy. This is just a regular lowercase times New Roman f. Please just make it like that if you like. That's it. It's an f. It doesn't have to be a calligraphist every time like this. Okay? Take it easy on yourself. Okay? So it's a lowercase f. Please never make it uppercase. Now, I have yet to see a single physics or math textbook where they call frequency uppercase f. Never. Lowercase all the time. Who remembers the unit for frequency? It's a person's name. You see it a lot. Okay, you either see it on radios, like old radios, or when you talk about the processing power of some processors, what do you talk about? Gigahertz. Yes. And it's probably the only unit in physics where it's a famous person's name, but it's actually how many letters? How many? 2, not just 1. Newtons is just what? Capital N. Joules. How many people remember what joules are? Capital what? Capital J, and so on. Hertz is actually what? H, Z. But the Z is what? Small, not both capital. Which might, okay, why do you think it's not just an H? Because there's another unit for what? For just H. Yeah, it's already, it's in magnetism. We'll study it a little bit. But H has already been spoken for. There you go. Capital H, capital Z. Gustav Hertz. An Austrian physicist who basically studied sonic waves and sonic booms and basically waves traveling in air mostly. Okay? So anything that has a frequency is always got to be measured in what? In, by the way, do you usually use hertz or do you use usually big scales? Big scales like what? What are kilohertz or megahertz or gigahertz or terahertz and so on and so forth? Yes. All right. What did you say the relation between frequency and period is? If one goes up, the other one has to what? Has to go down, vice versa. Which means if one of them goes up double, what happens to the other one? It goes down also by a factor of what? of double or half, depending how you want to really say it, which means, boom, that's it. This is always, by the way, this relation is so, this very simply, conceptually accessible relationship is so powerful. This is actually one of the defining equations of quantum mechanics and of how Einstein actually was able to analyze what the product, the energy of light depending on its frequency. Yes, that right there, the frequency of revolution or rotation or spinning, depending on what, and the time it takes to do it once. Can you make two equations out of this? Yeah, you can. How so? Depending on what you're trying to solve for. If you're trying to solve for f, what do you divide everything by? T. And if you're trying to solve for t, what do you divide everything by? F. Basically, you divide out the thing that you're trying to, you divide out the thing that you already know to keep the thing that you don't know and you're trying to get the value of. There we go. Frequency is the flip, or the, by the way, who remembers the mathematical word for flipping? Starts with R. Reciprocal, thank you. Frequency is the reciprocal. By the way, not, reciprocal is not, come on. What do you call sine with a -1 on top of it? Reciprocal is not inverse. When do you only use the word inverse? When we talk about numbers or functions. When we talk about what? Inverse, the word inverse. When do you only use the word inverse? When you talk about what? Functions, sine inverse, cosine inverse, tan inverse. You never call this t inverse. You just call it what? T to the power of -1, right? Or 1 over t. Everyone, never call these inverses. Inverse only applies to functions, not to numbers, not to symbols, only to functions. Those are called either reverses, flips, or reciprocals. Thank you. All right. I have a question now. Can I now go to the AC equation, and instead of using it in terms of t, can I use it in terms of f? I sure can. Let's derive yet another set of equations. We have this. What am I going to replace now? T. So it's what? There we go. How can I simplify this? Okay, hold on. Cross multiplying, if I multiply here and here. I'm just talking about how do I simplify this? Just this part. How do I cross multiply? Like, I'm assuming I don't know anything before. Imagine if I just gave you this. I think you're right, but okay, just hold on. Josh, what do you mean by cross multiplying? Because so far, for 10 weeks, cross multiplying only had to do with a what? When we're trying to solve for something in an equal sign. But how about if I'm asking you to simplify this? I know if I give you the answer, like if I give you the board, you're going to get the right answer. But I want you to explain to us what do you mean by cross multiplying. Thank you. So in a way, you're telling me to make this one a fraction, right? Which in a way, when you flip, you end up doing what? Cross multiplying. I totally get it. I'm just worried about the what, because we use that word. We use that word cross multiplying in a very specific situation. Equal, equal, equal when you're trying to solve for a variable. But good on it. So what do I do now? Not much. I just flip, and these, as he said, distribute that square on the 1, which is still 1, and the f squared. So, all right. And you just end up doing that. Go ahead. What's 1 times 1? 1, which means no need for a fraction here anymore. It just simplifies to that. Done. So now I have what? I have an equation of AC, but in terms of only what? What are the only variables here? By the way, pi is not a variable. Pi is a constant of this universe. What are the only variables here? Radius, the size of the circle, and frequency. So instead of taking the time, instead of worrying about how long it takes to spin, I'm asking you how frequently it spins. In 1 second, though. And by the way, everyone, just so you know, Hertz is always measured in how much time? 1 second. So, okay, question. What does it mean to say that Mr. Ramadan can tap his hand at 15 Hertz? What does that mean? 15 hertz. What does that mean? I can tap my hands how many times? 15 in? How about 15 megahertz? What does that mean? What's a mega? Million. So 15 million cycles in still how much time? Every time you hear hertz, you are scaling it always to 1 second's time. Never more, never less. All right. Okay, all good? All right. Okay, let's do some demos. Come on. An athlete in a what? In a hammer throw competition, like in the Olympics, swings the hammer with uniform circular motion clockwise as viewed from what? From above. Okay, let's just sketch a circle that spins which way? What does clockwise mean? With or against the clock? With. How about against the clock? What do you call it? Counterclockwise. CW is clockwise. CCW, counterclockwise, is the other way. So go ahead. Let's just sketch a circle. So, which means it's going to be spun this way. This is it. All right. But again, that's viewed from above. Okay. Oh, what's the speed of revolution all the time until he or she throws it? 4.24. So the whole time, the hammer at the end of the hand is spinning at 4.24 meters per second. At a distance of how much? So that means technically the center of the circle is the line running through them, and then you've got 1.2 what? 1.2. By the way, 1.2, is that the arm length? No way. By the way, you do know that the arm span is roughly half of your height. So 1.2 times 2 is what? No one is 2.4 meters, but that's until the end of the hammer. You see what I mean? That's hand plus hammer, okay? All right, so right here, go ahead, everyone. Let's just put 4.24 here, anywhere, as long as it's representative of the speed. And then from here to here, whoops, from here to here, that's 1.2 meters. Okay, what's the question? Oh, at a given instant, the hammer's velocity is directed south. Okay, we're looking above. If you're looking above, which way is north? Yeah, exactly. So technically, geographically speaking, north, east, west, south. So go ahead and just make a quick grid here. Oh, sorry. Like, okay, whatever. North, east, west, south. So apparently, where here, everyone, where here would the speed or the velocity of the hammer be directed towards the south? Who knows where to point on the circle? I want you to basically tell me, where do I put a dot on the rim of the circle such that that dot is moving towards the south? Not located south, moving perfectly towards the south. Ammar? Okay, I'm gonna move my finger. You tell me when to stop. Right here. Because here, remember the V diagram? If it's here and he releases it, how does the hammer go? In or tangent? Tangent. When you release, things go tangent. Things fly away, not in, fly away. So that means this is it. Yep, there we go. Boom, that's it. Okay, that's the first part of the question. The second part is easy. What's the centripetal acceleration at that instant? Do I have all the information I need for one of the equations we derived today? Can someone tell me which equation am I going to use? Because I taught you 3 equations today. The very first one and 2 more we derived on our own. Are you given any frequency information here? Are you given any period information here? Are you given just speed and radius? Done. That's it. Go ahead. AC equals V squared over R. Capital R or small r, whatever you like. All right. 4.24 squared, please don't forget it, over 1.2. You? All right. Who's got this? That's about 4.24 is slightly over 16, and divided by 1.2, 10 point something. How much? How much? 14.98. In what unit? It's an acceleration. So it's meters per second squared. Now, sig figs, I was about to. 3 and what? 2. What's this to 2 sig figs if you cut it right there? This is almost 15. What did they say in the question? How come they said west? I thought it's moving south. Come on, everyone. By the way, I'm not going to ask you to tell me directions. But why is the question saying west instead of south? Come on. Someone other than Ammar, please. Why is the question, why is the answer having west in it, not south? I'll give you a hint. Look where that dot is, and remember where AC always points. Come on. Other than Ammar. Josh. Everyone, look. Yeah, go ahead. Yes, if you are here, your speed is which way? Your speed is south. But acceleration is always what? Into, which in this case would be moving what? Sorry, not moving. Pointing what? There you go. You got it. Okay? That exactly. South is the motion direction. West is the what? Pulling in direction. Yes, acceleration inward direction. Nice. Which, by the way, is interesting. They're always got to be at what angle to each other? They always have to be 90 because tangent and radius are always 90 degrees to each other in any curve you ever do in your life. All right? Okay, another one. This time you're asked for the speed of rotation of the ball. A ball on a string moves in a horizontal circle of radius 1.4. That's how big it is. It's being pulled in with a centripetal acceleration of 12 meters per second squared. How fast could it be going? Which equation do I use? Equation 1, equation 2, or equation 3 from today? Equation 1, the easy one. Okay. Do you think we need a diagram? You could. You are more than welcome to do so, but I think it's straightforward. So go ahead. AC equals V squared over R. Okay. What do I know of these three? Come on. I know AC. And I know R. And I'm solving for V squared. How do you solve anything like this? Cross multiply. Now you crisscross. So, oops, sorry. Cross, cross. So we get V squared. Nice. Just a very quick 12 times 1.4. So V squared equals, what's 12 times 1.4? You mean the final answer? 12 times 1 is 12 times 4 point, that's 16 point. 16.8, yes. And the square root of this guy is 4 point. What's the specific situation? 2 and 2. So only one more digit I need. 0.1. How many people got 0.1 after rounding? 0.1 it is. In what unit, though? Is this meters per second squared? No, it's meters per seconds because it's a spinning speed. Nice. So far, so good. All right, next one. Is it more or less the one we just did? Yes, but this time you're asked for what? How big is the circle? How big is the radius of the circle? Okay, so AC again. V squared over R. So this time, I still have my AC. No, it's not 22, sorry. It's 7.8. 7.8 over 1 equals 22 squared. Please remember the square over R. Another crisscross. So, boom, boom. So 7.8 Rs. What's 22 squared? That's 484. So we just R equals 484 over 7.8. How much? Anyone? 60 something, 62. Okay. But 2 sig figs, so it's 2, 62. In what unit? Just radius. Meters. It's a distance. No speed. 62 meters. Okay, one more. Okay. One with period and frequency. A research apparatus called a centrifuge. How many people have heard of centrifuge here? How many people did biology here, grade 11, grade 12? Do you know how they do blood analysis? How many people have seen, how many people know people who are like lab technicians or went to fancies, pre-health? How many people what a centrifuge does? How do they analyze the components or the constituents of blood? What do? They put it in a test tube, and then what do they do with the test tube? They spin it. What does the spinning do? Yes. Depending on the density, the centripetal force separates it into what? Into basically into layers. What layers does blood have? You've got plasma, you've got the proteins, and so on and so. So basically, that's what they use it for. So apparently, the acceleration is how much? 3.3 times 10 to the 6. That's fine. It's very fast because it's very what? It's very small. Remember, when you spin something small, you can actually what? You can spin it very quickly, which means you're pulling it with a high tension compared to the radius of the motion. Good. Question. The centrifuge has a radius of only 8.4 centimeters. All right. Calculate the frequency of the centrifuge in both hertz and in what? In revolutions per minute, or RPM, like they use for car engines, RPM. Okay? All right. So what equations do we have here? Let's think. We've got the AC equation. Come on, everyone. Do we have the AC of this problem? Do we have the acceleration of this problem? Yes, we do. Okay, we got the AC. Do we have the speed? No, speed. We don't have it, and also we don't need it. Apparently, the question only wants what? Do we have an equation relating acceleration to radius to frequency? We sure does. It's the third one we came up with. You see, that's the power of what? Of having an equation ready instead of having to do how many equations? Everyone, if you did not have the third equation, how many equations we have to do? It would be a two-step equation. It would be a two-step problem, sorry. So let's do the equation. AC equals what? 4, come on, pi squared r f squared. Perfect. What are we trying to solve for here? The only thing that we don't know. We are solving for, come on, f squared, which means, do I square root first or divide first? You never square root first, because BEDMAS tells you to do it at the end. So basically, f equals a big square root at the end, but then you have to divide. What do you divide by what? Can someone tell me what's going to go on top? AC goes on top, because everything else goes under 4 pi squared r. All right. What's my AC? By the way, remember, everything has to be standard here. You've got centimeters, you've got whatever. Everything has to be standard. Unless you're trying to get something other than hertz, then fine. It doesn't have to be standard. All right. So what's my AC? It's 3.3 times 10 to the 6, like times a million. All right, that's fine. Over 4 times 3.14 squared times, what do I do now? Change it to meters by dividing it by 100. So really, it just becomes 0.084. Go for it. Please do it very slowly. Unless obviously you have the double display Casios or Sharps, then fine. But if you have a single display, please do it step by step. Like basically, I would recommend you do this part first. All right. I'll show you my way with a single display, because that might be relevant to so many of you. There we go. All right. So 4 times 3.14 squared times 0.084. Everyone, that right there, listen up. That right there is my what? Is my denominator. I'm going to flip it and multiply it by 3.3 times 10 to the 6. So I flip this way. Look, 1 over x, everyone, flips. Boom. Times 3.3 exponent 6. Is that my number? By the way, could that ever be? Actually, I'm not saying things could not be up to this frequency, but that's way too high for what, for the revolution. What do I do with this number? Square root it. Actually, no, 9. Oh, I think you did not put the whole thing in brackets. Yes, yes, you always have to put it in brackets. Oh, did you? Oh, perfect. Yes, it makes sense. Everyone, when you don't put it in brackets, it's not going to square root the what? It does not square root the power of 10, which changes everything. Yes. So that, yeah, so what's the sigma situation? 2, I think. Yeah, 2. So that would be what? Well, technically, that's very close to what? 1,000. Yes. If you cut, it's 99 point. Well, this is, okay, this is 9 point. No, oh, sorry. 9.98 times 10 to the 2, right? In hertz. But technically, that's what? That's very close to 1.0 times 10 to the 2. Oh, sorry, yeah, you're right. Times 10 to the 3. 1,000 hertz or 1 kilohertz of spinning.